Okay, let's make some sense out of the intermediate value theorem. So basically what this says is that if we have two x values, a and b, and if you evaluate our function f at a and at b, they have opposite signs, which means that f of a could be positive, f of b is going to be negative. Or it could mean between a and b, maybe f of a is negative, f of b is positive. Then there has to be some value that fits in between a and b. We'll call it c. We're not exactly sure what it is, but it's somewhere in between a and b where f of c equals 0. So let's think about that. Because we're dealing with polynomial functions are both smooth and continuous. It's that continuous trait that we really need to know about. All right, because they're continuous, that means that you can't draw a polynomial function without picking up your pencil. So if I start at a point that's above the x-axis, and I want to get to a point that's below the x-axis, somewhere in between a and b, I have to cross the x-axis, or I have to have a y value of 0. Same thing if I start below and I have to get above the x-axis to connect these 2 points together. Well, I have to cross the x-axis somewhere in between a and b. That's all it says for the intermediate value theorem. We can't pinpoint exactly where c is without more work. All right, so let's use this intermediate value theorem to show that this first example is a little bit more difficult, but that given this polynomial function, we have at least 2 zeros between 1 and 4. So what I'm going to do is I'm going to evaluate this function at 1. So that means replace each of the x's on the right-hand side with 1s. So 5 times 1 squared plus 3 times 1 plus 6. Now I've already worked this out, but this works out to be 5. F of 2, I'm just filling in some values. Nice integer values between 1 and 4. All right, I'm going to evaluate these in a similar fashion where I replace each of the x's with a 2, then a 3, and then a 4. I'm just not showing my work here. All right, at 2, works out to be 0. At 3, it works out to be negative 3. And at 4, it works out to be positive 2. All right, so let me think. 1, we were at positive 5, somewhere up here. At 2, we were at 0, so that's one of our zeros, or x-intercepts. At 3, we're below the x-axis because it came out to be negative. And at 4, it turned out being positive 2, which is somewhere here above the x-axis. So to show that this definitely has at least 2 zeros between 1 and 4, we can pinpoint one of them is right here at 2. Then you have to ask yourself, how can we show where the other one is? How do we know there's at least one more? Well, this comes between 3 and 4, that connecting these 2 points is going to require some sort of crossing the x-axis, or we can say by the intermediate value theorem, there has to exist at least one real 0 between 3 and 4. All right, one more quick example with this. This time with this f of x equals 7x to the 5th minus 9x to the 4th minus x squared, we want to show between 1 and 2, we have at least one real 0. So in a similar fashion, we're going to evaluate this function at 1 and at 2. Well, at 1, we get 7 times 1 to the 5th minus 9 times 1 to the 4th minus 1 squared. That works out to be negative 3. We do the same thing with 2, 7 times 2 to the 5th minus 9 times 2 to the 4th minus 2 squared, which works out to be 76. So from that, we can say by the intermediate value theorem, because one's positive and one's negative, or at 1, we're below the x-axis, and at 2, we're above the x-axis, somewhere in between 1 and 2, we're going to get an additional value where our function is actually equal to 0. So I hope this helps out by using the intermediate value theorem. Good luck.